slide, please. Okay, on behalf of my team, it's a real pleasure to be with you today to give you an update on how things are going. So. Okay. All right, so actually the title on this slide is a public service announcement for any NASA managers in the audience so they can sit back and enjoy the rest of the talk. Okay, GRAIL is a mission to study the evolution of the terrestrial planets. So the thing that I enjoy doing is looking at a planet and it's essentially being blown away by the beauty of the surface and going back and trying to solve the detective story of how it got to be like it is today. And I think I don't need to tell this community that we have just a plethora of amazing information that we've learned about the moon. We anticipated that LRO would be doing what it's doing, and it was our feeling that the missing piece of the puzzle was a truly, truly high-resolution study of the lunar interior. And that if we could do that, that it would raise the value of these different data sets. But also not only the moon, but other terrestrial planets as well, because the moon is the most accessible example of a differentiated planetary body of the terrestrial planet variety. So particularly the fact that this is going on at the time when Messenger is returning data from Mercury, and we're starting to get amazing information from Vesta, which is a protoplanet asteroid. Really, in the next 10 years, I expect our understanding of the accretion and evolution of terrestrial planets to really grow in leaps and bounds. So our mission objectives are to determine the structure of the lunar interior from crust to core, and to use that understanding to advance the thermal evolution of the moon, and then to extend that knowledge to understand other terrestrial planets. And we've divided our science objectives. I could talk about science for forever and ever and ever, but I'll just list them here and give you one example of our science floor and our baseline objectives: to study the structure of the lunar crust and lithosphere, to look at the asymmetric thermal evolution of the moon. Why did we have extensive melting on the lunar near side in terms of the Maria and not on the far side? The subsurface structure of lunar impact basins and the origin of mascons, and the evolution of crustal brecciation and how that related to the ascent of magmatism to the surface of the moon. And these are all examples of data that can be taken with very high spatial resolution gravity. Then going into the deep mantle, deep interior of the moon, we're trying to look at the deep interior structure of the moon from lunar tides and constraints on the core structure of the moon. And these objectives require information on the low degree structure of the lunar gravity field, and indeed their time variations. Okay, so just to give you a couple of examples here, I think this really exemplifies the kind of thing that we're going to be able to do with GRAIL. So for basin rings, there are a variety of models of what ring structures correspond to. And rather than just thinking about this in terms of block models, we think about it in terms of the energetics of the process and really what we can stand to learn about the physics of impact cratering, since it was the most pervasive mechanism or process to influence early terrestrial planets. And Jay Malash from our team did models of what the gravity signature would be in association with all of these models, and GRAIL will actually be able to resolve resolutions at less than the line width that's plotted up here today. So, so it's truly going to be transformative. Okay, there's been some interesting reanalysis of the Apollo seismic data which is tremendous. The signal to noise on that data is about 1, in some cases less than 1. And so there's still a great deal to be learned about the deep interior of the moon. If the moon does have an inner core that's separated from the lower mantle by a liquid outer core, then there could actually be some decoupling between the solid inner core and the mantle. And the plane, if you draw a plane through those, if you have a body in synchronous rotation, they will actually precess at the same 18-year lunar precession cycle, but those two planes will precess differently. And this manifests itself with small variations in the degree 2 coefficients of the moon's gravitational field. The C22 coefficient, which tells us about the shape of the lunar equator, and the C21 coefficient, which tells us about the orientation of the spin axis. And we will be able to model, to recover those two parameters, as well as a parameter called K2, which tells us about the nature of dissipation in the deep lunar interior. And we expect considerable elucidation about the deep interior structure of the moon. So how are we going to do this? So GRAIL is a 2-spacecraft mission. It is the first formation flying mission to another planet. It will sense the moon's gravity field by measuring the distance between 2 spacecraft. We will be varying the large scale separation between the 2 spacecraft between 60 and 225 kilometers. It's in an orbit very similar to the LRO orbit, and it's a very short mission. It's for a period of 3 months. The 2 spacecraft arrive New Year's Eve and New Year's Day, in keeping with the NASA tradition of doing all critical maneuvers on holidays so that you can't give your team a rest. Okay. There are a lot of radio signals on GRAIL. There's a Ka band link between the 2 spacecraft, which tells us the distance between the 2 spacecraft, an S-band radio link, which aligns time tags between the 2 spacecraft so that we can actually measure that distance. S-band up and down, which is essentially telemetry and lets us do orbit determination, and an X-band link that essentially takes an unmodulated tone signal from an ultra-stable oscillator and transmits it to the Deep Space Network, which allows us to measure the drift of the USO. And we do this because we need to get the timing calibrated, because this mission is all about timing. This is the lunar equivalent of a mission that's in orbit around the moon called GRACE, which is working today. GRACE uses GPS to do its timing. There is no GPS at the moon, and so we needed this solution. But now that we've come up with this solution, I should say that this is enabling for other missions to go to other planets that want to do coordinated observations that need very precise timing. Okay, so this is a very busy slide, but it speaks to the timeline of the mission, and we're essentially threading the needle trying to do this mission. So we're on track for launch in September. We're using Delta Heavy. We will, instead of doing a 3-day trip to the moon, we are doing a low energy trajectory to the Earth-Sun Lagrange point. And we're doing this for several reasons. One of the reasons that we thought of it initially was to save fuel, because if you go barreling to the moon, you got to slow down to get in orbit. And we wanted to use small spacecraft that were designed after a Lockheed Martin spacecraft that was a small spacecraft. The other advantages are that no matter what day in the launch window you launch, the 2 spacecraft get to the moon at the same time. So you can completely decouple your cruise operations from your in-orbit operations, which leads to great simplicity in planning. And it also allows the 2 spacecraft to get into orbit a day apart, so that you're not doing 2 orbit insertions in one day. We then get into orbit. The 2 spacecraft will insert into lunar orbit underneath the South Pole, and will, over the course of a month or so, decrease with their orbit with a number of small burns. Then the two spacecraft will line themselves up in this transition to science formation phase, and we'll start mapping the moon about the time of the Lunar and Planetary Science Conference next March. We will then map the moon for 3 months. And when I said threading the needle, it was we're trying to get between two eclipses, which the spacecraft isn't powered to do. Okay, next slide, please. Okay, so the performance of the investigation, this is a plot of surface accelerations and power here where, and these are errors, and wherever the error curve intersects the power curve, that tells you the resolution of the field. And without going into detail, will be 4 orders of magnitude better than Lunar Prospector, nearly 3 orders of magnitude better than LRO, and over 2 orders of magnitude better than Kaguya. And whenever you can make measurements orders of magnitude better than other measurements, the science is going to be transformative. So just some nice pictures of the spacecraft. This is when it was in one of them was in Lockheed Martin, and the solar arrays were deployed. Here are the two spacecraft side by side in the thermal vacuum testing chamber. Some of our accomplishments here, so all of the launch vehicle hardware is now delivered and on the launch pad. All the Grail flight hardware is now installed on the two spacecraft. Lori Garver came to see us last week down at Astrotech in Titusville. All the flight software is complete and loaded on the two spacecraft, and at this point there are no errors in the spacecraft and we don't expect any updates. So the mission is on cost, on schedule, on spec. Okay, and so now everybody can wake up because we have a guest investigator program. It was released yesterday. $450K for 2 years. We expect to select about 6 investigators. The proposal deadline is October 12th. Thanks to Jim Green for the money and Bobby Fogel for pushing this through. And the emphasis on this is going to be comparative planetology, using the information from GRAIL to advance our understanding of the moon and terrestrial planets. So I'm around, and please ask me questions about this. And the launch window opens on September 8th. So thank you.